We got a SPI bus interface running on the R32V2020 RISC CPU. Let's take a look at it. SPI bus is a fairly easy interface. It consists of data out from the host controller called master out slave in, which is very nicely named when you're trying to figure out which one is a transmit and which one is a receive when you have to hook things up. SDI or MISO, master in, slave out. All the names start with the master and then have the slave in it, but out and in are clearly labeled. S clock, which comes out of the master, and a chip select, which could be grounded in the example we have here, but we're driving it out with code. The hardware we're using is our SPI POTX2 card. It consists of a 7-bit dual potentiometer. You write out a 7-bit value to it and you get steps of 127 or 128 steps, and it'll go from 0 to 3.3 volts if you hook the plus and minus V up to the B and A pins of the pot. Can be done with jumpers on the output quite easily. The SPI pot we have installed is a 10K value part, although there are other values like 5K. The interface is capable of running it up to 10 megahertz, although with this RISC design we can't run it at that speed, and we'll take a look at why. It runs from 2.7 to 5.5 volts, which is fine with the 3.3 volt output, and they could be daisy chained, and it's on our 49 by 49 millimeter ODAS form factor with mounting holes in the corners. The SPI pot card is of course the slave, and the R32V2020 CPU acts as the master. The timing involved with the clocks can run up to 10 megahertz, although our granularity with our 50 megahertz clock is only 20 nanosecond ticks. So to create a 50 nanosecond, or in this case 45 nanosecond high or low, would be 3 clocks, which means we run at an effective rate of 8.33 megahertz. With an extra PLL output, it probably could be scaled up to 10 quite easily, and I've run it quicker than that. Ran it with 2 and 3 clocks, so it was a 10 megahertz rate, but 2 high and 3 low, and it seemed to work just fine, but that did violate by 5 nanoseconds the timing specs. The software interface consists of either 8-bit or 16-bit commands. The 8-bit command only gives you the ability to increment or decrement the value, and although that would work for the ramp example we have here, it wouldn't be a good general case. So we're using the 16-bit command, which means 16 clock cycles or bit cycles with clock and data have to be sent. First 8 bits are the command, the next 8 bits, 7 of which are used, are the data that set the pot value. For our initial cut of code, we wrote code that set the pot to the high limit and then to the low limit, and it was running at 1 megahertz, so that gives an effective time of 10 microseconds to do a high and a low write. Here was the timing when we ran at 10 megahertz. If you notice, the high and low are not symmetric. The high is 40 nanoseconds and the low is 60 nanoseconds, which gives 100 nanoseconds or 10 megahertz, but violates the timing as I noted earlier. And here's the timing that I settled on. It has 3 clocks high and 3 clocks low, or 60 nanoseconds, or a cycle time for clock, total time of 120 nanoseconds, or about 8.3 megahertz. With this timing, the high clock time is 60 nanoseconds, which is more than the 45 nanoseconds required by the spec. And the clock load time is also 60 nanoseconds, which is also better than the 45 nanoseconds required. Here's the code to write to the SPI pot. There's a couple of different addresses. You have to set chip select manually with this code. You also then write out to the data register. Since there's 2 writes, it shows up as 2 writes here, and there's a call to the wait for the TX ready cycle to happen. Pretty straightforward code. Took a little while to figure out how to make it work, especially since waiting for the TX ready really has to happen because it's so much slower than the RISC-32 CPU processor. And here's the code for waiting for the ready. In this case, we both wait for the ready to be not set anymore, because there's a delay sometimes depending upon when you write to it between the clocks of the CPU at 50 megahertz and the I/O clock. I was having that trouble, at least at a megahertz. May not be as much of a problem at 10 megahertz SPI, but waiting for it to get ready and then staying there until it's not busy anymore, that completes a ready cycle, and by that point you know the whole transfer has happened. The code writes a ramp value as quickly as the hardware can accept it, and the ramp goes from 0 through 127, so it writes a full single bit every step. And here's what that ramp looks like on the oscilloscope. It goes from 0 to 3.3 volts with a ramp time of 744 microseconds to get from low to high, and then it switches back immediately to low again. Here's the two sets of writes that have to happen. The first write is to the control register, and the second write is to a data value. In this case, the data value is 70, and the write of the control register at 00 writes to the first pot. Remember, this card has two pots, but I'm only writing one for this code. This was captured using Soleil logic with decoders for the SPI, quite a nice product. Had to run it at 24 megahertz to keep up with the 10 megahertz bit stream here. Don't know if 12 would have captured it, might have, but I haven't really tried it. Didn't have to get too many samples to get a single cycle here, but you can see that chip select gets reasserted again at 5.75 microseconds. It can write out every single value. So not a bad clip to move along, definitely quicker than I2C. The original SPI code came off the reverse -U16 U16 ZXopoly project, and they have a piece of SPI.VHD code up there. And this looks like it's a bunch of different processors. I'm not sure if it's related to MiSTer or some other similar sort of a project. But the SPI did pretty much work on modified, although if you look in my GitHub for the project, it's changed somewhat because I have different clocking than what the Z80 would have had. We're quite a bit faster with the RISC-32 CPU, and our clock for loading values is much more narrow. It's only 120 nanosecond clock. So it took a little bit of tweaking, plus it was originally written in Russian, and I translated it with the help of Google Translate to English, so it's been recommented in English. So you can take a look in our GitHub to see how it works, and the code would get you probably a pretty good, close to a working example. And definitely a tool like that Soleil with the open source SIGROC pulse view program to look at your output and then work your way through comparing it to timing diagrams will take you a long way to debugging something like this. This came up in just a few days. It wasn't really that hard. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.